So welcome again, everyone. Eric, are you ready?
I am. Yeah.
Okay, so let's before we start, let me just again remind everyone that we if there are any talks you'd like to hear, let us know. Today's talk is by Eric Blais. This is probably going to be the last talk for the spring, but we're happy to have another session this spring. If you have any ideas or recommendations, if not, we'll see you again in the fall. Some other announcements. Let me thank also all the other organizers that do all the work here behind the scenes to make this happen. We have Thomas Vidic, we have Anindya De, we have Gautam Kamat, and we have Clément Canon that work behind the scenes to make this whole operation function. What else? So welcome everyone. Again, today's speaker is Eric Blais. Eric is a professor at the University of Waterloo. He graduated in 2012 from CMU under the supervision of Ryan O'Donnell. His interests are in complexity of Boolean functions, sublinear time algorithms, property testing, monotonicity testing, which is something we'll hear about today. Before we start, let me quickly go around the table just to see who's with us. So we have Amit Levy with a group from Waterloo, with a big group from Waterloo. Hi, good to see you. Welcome, everyone. And we have Dawei Wang from University of Michigan. Hi, guys. We have Piyush with the group from Caltech. And here it goes. Hi, guys. Good to see you again. We have Sorachai joining us from Michigan State University. Hi, Sorachai. And we should have a couple more groups joining, but there's not here yet. So I suggest we just start. So again, I already presented Eric, and he can tell us today about polynomial lower bound for testing monotonicity. Thank you, Eric, for joining us, and feel free to go ahead when you're ready.
Great. Thank you, Oded, for the introduction, and thank you, everybody, for joining us today for this talk. What I'm going to be talking about is results on one of my favorite problems, one of the beautiful problems in property testing that got me interested in the area in the first place. That's the problem of testing if a function is monotone. So let's get started, and let's introduce our main event. There we go. The main object we're going to be looking at today is monotone Boolean functions. So a function is monotone if it satisfies the natural property that if you take any Boolean input and then you flip some of the zeros to ones, you can only increase the value of the function. You can never decrease it. So you flip some bits from 0 to 1, either the function stays the same or it increases value. And here we're looking at functions that only take two values, 0 or 1. So the only thing that can happen is you keep the same value or change from 0 to 1. Let me start by saying something extremely obvious. These Boolean functions have a lot of structure, and this structure has turned out to be interesting in quite a few different areas. So just to get some context, let's just look at two of the applications or two of the areas where monotonicity turned out to be quite interesting. So in machine learning, in learning theory, one of the fundamental problems that's still open is whether we can actually learn functions that have a reasonably concise representation in polynomial time. So in particular, if your function has a Boolean decision tree that computes it and the decision tree has polynomial size, can you actually learn the function or learn a good approximation to this function efficiently? And this is still open in general. This is one of the big questions, maybe the big question in learning theory. But for monotone functions, we do have a positive answer. So if your function is monotone and it can be computed by a small decision tree, then indeed we can actually learn this function in polynomial time. Completely different area, another famous result. One of the other beautiful problems in circuit complexity that we'd really like to solve is to figure out whether we can prove a super polynomial lower bound for the clique problem. If anybody has any solutions, I'd love to hear it. Actually, no, this is going to go on the internet, right? No, cancel this. I don't actually want to get emails about this yet. After someone verifies it, I'll be happy to learn about it. But what we do have is that we have this, again, this very special result if we're only looking at monotone functions. So if your circuit is such that it doesn't have any negations, another way of seeing this is, or looking at this object is saying it's a circuit where any partial circuit of this function always computes monotone functions. And if your circuit is like this, where the only functions computed throughout the entire computation are all monotone, then we know by Razborov's famous result that we do need a super polynomial size circuit to compute the clique function. So again, just this idea of having monotonicity really changes the problem, gives us additional structure that we can use to solve these problems. So having said this, it kind of raises a natural question, this idea of if monotonicity is such a strong structural property of Boolean functions, does it mean that we can actually check if a function is monotone or not? Can we distinguish those monotone functions from the other functions easily? Now, if I let you think about this for about 2 minutes, I think the answer quickly becomes apparent that the answer is yes. If I want to check whether a function is monotone or not, I can use a very simple but very useful property of monotonicity itself, which is that it's a very local property of Boolean functions. In other words, the function is going to be monotone if and only if for every edge of the hypercube, for every 2 inputs where I just flipped 1 bit to go from one input to the other, if it's monotone on those pairs. So now if you design an algorithm to check if a function is monotone, you're just going to go through all these edges, all the pairs of neighboring inputs from the hypercube, and check whether they're all monotone. So this runs in time that's nearly linear in the size of the Boolean function. And it's very easy to see that actually we have a linear lower bound for this, because you need to essentially check the value of the function on all inputs to make sure that you catch all functions that might be non-monotone. I could always take a monotone function and hide some 1 bit somewhere that I flip to change it to a non-monotone function. If you're not looking at most of the points, you're not going to catch this noise. So the starting point for the problem that we're actually going to talk about today is this idea of saying, okay, what if I remove this annoying technicality? What if I make your problem a bit easier in the sense that now you only have to distinguish monotone functions from the ones that are far from monotone? Can we say something more about how efficiently we can do this now? And in order to say this, what we need to do is we need to actually define what we mean by far from monotone. And here we're going to use the standard property definition, a property testing definition, which happens to be a fairly natural, or I would argue like the natural notion of distance to remove this annoying condition of just flipping 1 or a few bits. So we're going to say here that for some parameter epsilon, you're epsilon far from being monotone if you need to change an epsilon fraction of the value of the function. If you need to change the value of the function on an epsilon fraction of the possible inputs to turn it into a monotone function. So another way to say this exact same thing is if you take your function and if you take any monotone function and you look at this number of points on which they disagree, you want this to be an epsilon fraction of all the 2 to the n points of the hypercube. So now the monotonicity testing problem can be phrased precisely as saying, okay, we're going to be asking about how many queries we need to distinguish the monotone functions from the functions that are far from monotone when we consider randomized algorithms that can make some error, but a non-trivial amount of error. So say 99% of the time you want to be correct. We're going to look at the queries just because it happens to be a simpler measure to look at than running time. Also because for us we're interested in lower bounds, so lower bounds on query complexity give us automatically lower bounds on running time. But it turns out even for the upper bounds we'll be looking at, the query complexity really determines the running time. There's no hidden complications in the algorithms themselves. Okay, so we've got our problem. Let's see what we can say about this. If we want to start with the most obvious tester, what we should do is take the algorithm that we had for checking monotonicity and see if we can translate it to this setting of property testing. So here we said if we were working with a deterministic algorithm that always had to be correct, it had to look at all the possible edges of the hypercube, check that the function was monotone everywhere. Now we can try to say, okay, well maybe instead of checking all the edges, maybe what we can do is sample them at random. So look at a random pair of inputs that differ on only 1 coordinate, check if the function is monotone on this pair. If it is, you say, okay, I'm going to pick another edge, I'm going to check again. Do this some number of times, and if at any point you find an edge where they have different values, or the function is not monotone on this pair, then you can automatically reject the function and be confident, actually know for a fact that this function is not monotone. So the picture here is one example of this, where the gray points represent the points on the hypercube that you didn't look at, so it doesn't matter what the value the function has on those points. Just this one edge that we looked at has 2 points where black was 1, white was 0, and going upwards was flipping 1 bit from 0 to 1. So we have a violation of monotonicity right there, and we know the function is not monotone. Okay, so we have this very natural tester, but now the question becomes, how many times do I need to do this to actually be guaranteed that with high probability, if you were far from monotone to start with, that I will catch one of those violating edges with high probability? And this turns out to be a highly non-trivial problem. So the reason this is non-trivial is we're talking about 2 different things. When you're far from being monotone, we're talking about the fraction of the points in the hypercube where the function needs to be changed to turn it into monotone. And when we're talking about the edge tester, we're actually talking about a completely different measure, which is the number of edges that are actually decreasing, the number of violating edges. So this main result, the first main result for testing monotonicity, relates those 2 measures. What they showed is that this edge tester that we defined, it's a valid monotonicity tester if we repeat it essentially n times. So here I'm going to be ignoring the epsilon from now on, so think of epsilon as a constant. I want to test whether you're monotone or really far from monotone. You'll still need n queries to do this. And the argument goes by shifting argument. It's very elegant, very beautiful. This is kind of the first of many pointers I'll have for this talk to just encourage you to go look at some of these other results. It's really nice, non-trivial, but once you have it, it's the clear, beautiful argument that you don't forget afterwards. But what they showed in this paper was that this analysis is tight. So the edge tester will not catch every function that's far from monotone if it doesn't have this linear in n number of samples or queries. But it doesn't say anything about the problem itself. So there's this question of whether we can actually have algorithms that do better than this. And in fact, we can actually consider another class, a wider class of algorithms that's quite natural, which removes this condition that we only look at the edges of the hypercube. It says, okay, let's go back to actually our original definition of monotonicity. We were talking about different pairs where we flipped some numbers of 0s to 1s, and you're monotone if and only if the function does not go down between those 2 points. So we can actually design pair testers that actually follow this more general definition by picking some comparable points x and y that are comparable to each other. So y is obtained by flipping some of the 0s of x into 1s, but not necessarily just one. It could be an arbitrary number of them. You define some definition over all these pairs, and again, you just check that the function is monotone on this pair. So for a long time, it was completely unknown whether this algorithm could be any better than the edge tester, or whether you gain anything from this more general framework. But recently, it was shown that you could do better. Chakrabarty and Seshadri were the first to show that actually pair testers can do strictly better than linear in n number of queries. And very recently, Kottminzer and Safra showed that, in fact, they can do quadratically better. So you can get by with square root of n queries to actually test monotonicity with these pair testers. This is my second pointer. Look into this. This is absolutely beautiful. It uses these ideas that are completely surprising, non-intuitive, in the sense that it connects the problem to isoparametric inequalities. So now, this is completely unrelated to the rest of the talk, but let's take a short detour about this, just because it's so nice. The classical isoparametric inequality says if you have a certain volume and you want to fit it into some shape, any shape that you want, it could be like a cube, it could be a sphere, it could be like this weird shape, but you want to minimize the surface area of this shape. It turns out we have very tight inequalities that say actually you can't do any better than the surface area of a sphere with that volume. And in fact, anything that has surface area close to this will be close to a sphere. So this is something in this continuous space, but we can think of the exact same analogies over discrete spaces like the hypercube. And these inequalities would say something like, if your function has a certain number of 1s, and we measure the boundary in terms of the number of edges of the hypercube, where the function is 1 on one endpoint and 0 on the other endpoint, we're again going to have this inequality that says you're going to have some number of these bichromatic edges. So all of this is all just classical isoparametric inequalities. And the reason this becomes really interesting here is Chakrabarty and Seshadri observed that we have similar behaviors that come up when we consider functions that are far from monotone. And in this case, the distance to monotonicity corresponds to what was the volume in the classical setting. And now the number of edges, the surface area, is no longer just bichromatic edges, but it can be measures related to the number of decreasing edges. So somehow we have these inequalities that say you have to have a minimum number of decreasing edges, and if you have a very small number of decreasing edges, you must have some additional structure. It's not just any functions that can satisfy this, it's only very specific kinds of functions. In the same way that in the classical case, anything that had very small surface area was close to a sphere.
Eric?
Yeah.
Quick question, is it really about edges or about longer paths, as you would expect from a pair tester?
Yeah, so it's about edges, but it's not about the number of edges. So here I'm oversimplifying it. Really, it's about different notions of the surface area of a function. But what they do is they now show that the way we use this is you're going to run the edge tester first, but not as many times as you would expect for the edge tester by itself to work. And if somehow you didn't find any violations, we now have this promise that the function is far from monotone, but in some sense has very small surface area. So it must have this structure, and then you can use this structure to actually argue that now these longer paths are likely to actually catch these violations of monotonicity.
Thanks.
Yeah, so it's very cool. It's still worth investigating. I still don't completely understand how these two ideas connect. I feel like there might even be more to say about this, but here we have at least 5 experts on this slide who could probably tell you a lot more about this. But okay, so this is this path tester, and we do much better. And we're left with this big question, which is still open. Is this tester optimal? So now we've shown we can do better than the edge tester, but can we still do better than this? So now let's flip the situation around a little bit, and let's look at lower bounds. The first thing we can say is that if you really want your tester to accept monotone functions, so you're allowed to make errors when you're far from monotone, but you accept erroneously. But if your input function is monotone, you absolutely have to accept. You're not allowed to have error in this case. If we consider these classes of testers, we now are in the setting where they have one-sided error. So if we look at testers that have one-sided error, and on top of that I add another constraint, which says that actually your tester must decide all the points it's going to query before it begins. So you tell me what you're going to query, and then in one batch I'll give you the value of the function on all those points. And so you're not allowed to adapt which queries you want to make based on the answers that I give you. If we consider those testers, actually you can't do any better than this Coate-Minzer-Safra algorithm. And we can also check that actually their algorithm satisfies this condition as well. It's only going to pick some pairs, it's going to have some distribution on them, check it, and it's always going to accept monotone functions. So in this class of tester, this algorithm that we saw is optimal. So now let's start seeing actually some of the ideas. How would you prove something like this? So the core idea is very elegant in this case. It says, okay, somehow it feels like the number of edges that, in order to actually catch the fact that you're not monotone, you need to find 2 points that are comparable and where the function is not monotone on this comparable pair. So ideally, maybe you can think of it, you want to find an edge where the function is not monotone on this edge. So if we're trying to build the lower bound for this problem, really what seems like the natural way to proceed is to find a function that has as few decreasing edges as possible. In this case, it happens that we know exactly which function satisfies this, the anti-dictator function. Take the function that's going to pick one of the coordinates at random, and the output of this function will always be the flip value of this coordinate. Everything else gets ignored, you just return the flip value of this. This has only 2 to the n out of n times 2 to the n total edges that are decreasing. So this is actually the minimum we can obtain. So you might say, okay, so if we consider this, maybe we can argue that any tester will have to make lots and lots of queries to find one of these one of these edges that is decreasing. And here, actually, it's not quite true. In fact, if I just want to design a tester that's going to give you a certificate that this function is not monotone, I can do this very easily. Query the L0 point, query the L1 point, and if you're the anti-dictator function, this is going to be an evidence that you're not monotone. It doesn't satisfy it on those 2 points, no matter which dictator you chose. Okay, so this kind of feels like it's killing our example, but it turns out there's a very simple fix for this. I'm just not going to allow you to query those points. How do I do this? Oh, I think I made a mistake. So what I want to do is I want to truncate the function so that actually when we're looking at the top section of the hypercube, it always takes the value 1. And at the bottom of the hypercube, you always take the value 0 down there. So then what happens is that all the action for this function is in the square root middle layers of the hypercube. And we're going to call these the balanced queries, the balanced inputs, where you have roughly the same number of zeros and ones. Now, if I do this, it turns out that I actually modify the function at only a tiny fraction, a little o of 1 fraction of the entire hypercube. So anything that was far from monotone before will still be far from monotone. So if I take these truncated anti-dictator functions, they will be far from monotone still. But now, what happens is, if my tester queries any unbalanced input, it knows already what kind of answer it's going to get. If it queries anything that's up high in the hypercube, like the all ones input, I'm going to return the value 1. So there's no information gained by considering these queries. And if I query anything that's very low in the hypercube, I get the value 0. So again, there's absolutely no reason to query this. Those points will never give me certificates of non-monotonicity. So in effect, what we're doing is we're forcing the algorithm to only choose queries in the middle square root n layers of the hypercube. And now if we think about this, now essentially you can compare 2 inputs that have square root n bits that are different than each other. The probability that you caught the dictator coordinate in those square root n bits is going to be 1 over square root n. And you need to repeat this essentially square root n times in order to actually catch the anti-dictator bit. So get your evidence that the function is not monotone and be able to reject the function. So there's actually a little bit more to this, to analyzing not just a pair of queries, but saying any set of square root n queries that you choose, again, you won't catch the dictator, you won't catch any pair in there that are comparable that contain the dictator coordinate with high probability. But this is the idea. This main idea will be reused. We'll use it in our own proof, this idea of looking at truncated functions. Good. So now we've got this lower bound for one-sided error. The next natural question is to ask, okay, what about if we allow two-sided error? So now you don't have to find evidence that you're non-monotone. So you're allowed to reject monotone functions with low probability. It turns out for this class of functions, we also have a square root n lower bound. And this was established only last year by Chen, Day, Servadio, and Tan. And what they do for this, it has to be a little bit more of it's a more complicated task in the sense that it's not enough to show that it's very hard to find a certificate against monotonicity. Now what they need to show is they can come up with 2 distributions, a yes distribution of functions that are monotone and a no distribution of functions that are far from monotone. And no matter what set of Q queries you choose, you're not going to be able to distinguish between the two. The 2 distributions of functions will look the same under those Q queries. And this is what's called oftentimes Yao's Minimax method, or similar names. But the idea is very intuitive. It's something that should be natural. So if you have this fact that for any Q queries you could tell your distributions in both the yes case and the no case look identical or nearly identical on this set of Q queries that you picked, then there's no way to build any distribution over the set of queries you could make that could actually distinguish between these 2 cases. So here specifically what you're trying to show is that you find these distributions yes and no, such that for any input that you choose and for any set of possible responses, the probability that you get one of those responses is nearly the same in both the yes and the no case. So the difference in these probabilities of landing or of obtaining one of those responses is little o of 1 for all these. So this is essentially where we stand with the lower bounds. There's one more thing I can tell you, which is that any lower bound for non-adaptive algorithms gives you a corresponding lower bound for adaptive algorithm, but where you lose a log n factor. So the best lower bound we have for adaptive algorithms is only log n, which follows from the Chen, de Cervedio, and Tan result. So we now have an exponential gap between the best upper and lower bounds for this problem in this general setting where we allow two-sided error and we have adaptive algorithms. So then we have this question, well, is it possible that adaptivity could actually help us? Is it conceivable that log n is the right query complexity for testing monotonicity? And this is one of the other reasons I really like this problem. It's because, yeah, actually, there's good reasons to believe that additivity could help. Actually, you could argue both ways. This is why this is really fun. There's really good arguments saying why you shouldn't. Now perhaps we have a bit more than a good argument, but even before the lower bound, there were good reasons to believe that adaptivity shouldn't help. But there's also at least one good argument for why adaptivity should help. And this argument is binary search. So in a way, so this binary search, what can we use it for? We can use it to find bichromatic edges for a given function with log n queries. So you give me any two inputs where the function has different value. I can build the hybrid strings between those two inputs, and I can do this binary search through this list to actually end up with two inputs that differ in only one bit and for which the function has different values. So with log n queries, I can now find a bichromatic edge. And in a way, we were arguing before that it seemed like, at least in some cases, what might be difficult for the algorithms is exactly this case, that you might not have many bichromatic edges. You might not have many decreasing edges. Maybe, like, at least for the edge tester, it might be that whenever you pick edges, you end up seeing the same value in both cases. And this was maybe why it was so expensive to actually do monotonicity testing. So now I'm giving you a procedure that actually will find a bichromatic edge much more efficiently. And in fact, we can randomize this to get some distribution over the bichromatic edges. So now it seems to change the game quite a bit. And in fact, it does. If we look at the examples we saw for non-adaptive lower bounds, we get much stronger upper bounds as soon as we get adaptivity. If you wanted to make sure you reject the truncated anti-dictator function with few queries, you can now do this. This is just essentially because this binary search will probably stay in the middle layers. With high probability, this search stays in the middle layers of the hypercube, and so the edge that you end up finding happens to find the dictator coordinate with only log n queries. So here we have a one-sided adaptive tester that rejects this anti-dictator function with only log n queries. And now you might say, okay, so what about the lower bound we had for two-sided errors? So this construction used linear threshold functions, in fact, a class of regular linear threshold functions, where essentially what happened is you would assign a weight at random to each coordinate, and then for every input, you would just sum these weights times the value of the coordinate, and just check whether or not you pass some threshold. Now, the lower bound was obtained by showing that actually if you choose these weights very carefully, so that in one case they're always positive, but in the other case they can be negative with fairly high probability, then actually making sure the moments of your distributions on these weights match implies that you won't be able to distinguish between these two functions. However, we've shown actually in this paper that if you have additivity, now once again I can use my binary search, and I can argue that you'll find one of the decreasing edges, not just a bichromatic one, but a decreasing edge with constant probability every time you do this search. So again, we have log n query complexity exponentially better than what we did for this other class of distributions or class of functions that were hard to test in the non-adaptive case. So of course, all of this buildup is to tell you that even though it seems like adaptivity can bias something, it cannot actually bias this much. We cannot get an exponential speedup with adaptivity itself. So the lower bound we're going to show is not tight, but we show that you need roughly n to the 1/4 queries for any algorithm that tests monotonicity, adaptive or not, one-sided error or two-sided error. Any algorithm you come up with will have to have this query complexity. And so for the rest of this talk, what I wanted to do is kind of give you an overview of how we obtained this proof, but this is a nice spot to actually stop and ask if there's any questions about any of the results or anything else before we dive into the details. Going once, going twice. All right, that's it, we're going in. What we're going to do is we're going to use, again, what's called Yale's method. But to get a lower bound for adaptive algorithms, we actually have a stronger requirement. So before we were saying, okay, what we need to show is that the probability you get any set of responses is roughly the same under both distributions. Now we're going to say something much stronger. We're going to try to show something stronger. We're going to try to get two distributions. Again, one which is on monotone functions and the other one which is on functions that are far from monotone. But now we want to show that for any queries that you come up with, any set of Q queries, and any possible response that you could get. So not just set of responses to say, oh yeah, it was one of those responses or not, but any individual response that you can get. The probability that you see this response in the yes case is roughly equal to the probability that you get the same response in the no case. So we're going to, by roughly equal, I want to say that they're equal up to this multiplicative factor of 1 plus little o of 1. And I allow a tiny, tiny additional additive error to this term, but only on the order of less than 2 to the minus q. So here, this is now much stronger than what we needed for non-adaptive algorithms. And as we saw by the upper bounds that we had, we actually have to construct mu distributions to hope to get this, because what we had, at least for the linear threshold functions that were considered, we had this log n upper bound. So the name of the game is, how can we find those distributions? How can we find these functions that on the one hand are monotone and on the other one are far from monotone, but they somehow look the same in this very strong sense to any adaptive algorithm? And the way we're going to try to do this is actually through an idea that, at least I would like to argue, is fairly simple. What I'd like to come up with is a family of monotone functions where I can flip a small set of coordinates at random, and I get a set of functions that are far from monotone with high probability. So take this set of monotone functions, but then say, okay, I'm going to apply this function, but I'm going to flip it in some of the dimensions, some of the coordinates, so that it's going to be actually anti-monotone on those coordinates. And then I'd like to say, even if I flipped only a small number of coordinates picked at random, I'm still going to end up with something that's far from monotone. So for example, if I take the dictator function, I could say, okay, take the family f here to be the family of dictator functions. And then take this family f superscript s to be the functions where it's the dictator function, but I flipped a set s of coordinates. So this means that if s includes the dictator coordinate itself, it's going to be the anti-dictator function. Otherwise, the other coordinates don't do anything, so you're still going to be the dictator function. So in fact, for this family, if I chose the dictator functions, I would need s to be very large, on the order of n, in order for the flipped functions to be far from monotone with high probability. With the linear threshold functions, we have the same problem. Again, if you go through and examine what happens, you realize that in order to turn a monotone linear threshold function where the weights are roughly all the same into one that's far from monotone, you need to flip, again, a constant fraction of all the coordinates. So this tells us once again that dictator functions, linear threshold functions will not help us. But the hope is that we can actually find some other distribution or some other class of functions where we can do much better, where you can flip maybe as little as square root n coordinates and end up with a function that's very far from monotone. So is there such a function? And how would we actually go about trying to find one of these functions? The answer, it turns out, is in noise sensitivity. So it turns out that the property that we're looking for in our class of monotone functions is that they're very noise sensitive. Formally, the definition of noise sensitivity says that your function f is noise sensitive or has noise sensitivity at some noise rate delta, determined by the probability that if you pick a random input, and then you just add noise to the input by flipping each coordinate with probability delta, the probability that when you do this, you actually flip the value of the function. So another way to think about this noise sensitivity tells us the probability that we get the wrong value of the function if when we get the value of the function, we get the right value, but we don't get the right input. It gets actually changed with some probability. This noise sensitivity is one of the fundamental measures in the analysis of Boolean functions and turns out to be extremely useful in this case because it actually matches very closely with what we're trying to do. So in particular, if you have a monotone function and the noise sensitivity for some parameter delta is constant, then what happens is if you pick this set S, where by including each coordinate with probability delta, and then you flip on those coordinates with constant probability, the resulting function will be far from monotone. So somehow this noise sensitivity is exactly what's capturing this ability to become very far from monotone by flipping on only a few of the dimensions of the coordinates. So now we can restate our question to say, okay, so what we wanted this very useful class of monotone functions. How can we get it? Well, it turns out formally what we're asking for is a class of monotone functions that have constant noise sensitivity, even for very small subconstant values of delta. And we have such a class of functions thanks to Michel Talagrand originally. And they're Talagrand's random DNFs. So here this construction is going to be fairly simple. What we're going to do is we're going to pick random conjunctions. I'm going to take the and of a random set of coordinates. And here, just to make the parameters work out right, I'm going to pick square root n of the coordinates. So you're going to pick square root n coordinates at random independently, so you might actually pick the same one twice. This doesn't really change anything. And then you take the and of this, and this gives you a random conjunction. So Talagrand's random DNF just says, repeat this process, draw 2 to the square root n independent random conjunctions, and take the OR of these conjunctions. So each conjunction on a random input is going to be satisfied with probability roughly 1 over 2 to the square root n. So this means that by choosing this number of conjunctions, I end up with a roughly balanced function. So this is kind of why these parameters were chosen. But it also happens that actually by choosing these parameters, we get this really nice high noise sensitivity that we were hoping for. This is a result of Mossel and O'Donnell. They showed exactly what we wanted to get for this construction, that with constant probability, if you get a function from this random, if you draw one of these Talagrand's random DNFs, you end up with a function whose noise sensitivity is constant, even for delta as small as 1 over square root n. And so it means in particular that even if we flip square root n coordinates chosen at random, and we look at the resulting function, it's going to be far from monotone with high probability. So we have actually the two distributions we're looking for now. In the yes case, what we're going to do is we're going to pick one of these random DNFs. And in this case, this function is monotone because we always took the and of the coordinates themselves. We never negated anything. So in this yes case, we have these monotone functions. In the no case, we're going to flip the function on this random set of coordinates that we picked. And with high probability, we end up with something that's far from monotone. So now the task is, can we still distinguish between these two classes or these two distributions of functions? And one twist, I promised we would use this again. We won't actually see the reasons why here, but actually it turns out that we do want to force the queries to only be balanced. So we're going to actually modify the construction a bit to take the truncated version of Talagrand's random DNFs. And in the no case as well, we still end up with something truncated. Now we have our task. So what we want to show is that now for any queries that you picked, so you get to pick roughly n to the 1/4 queries, inputs. Now you have to pick them to be balanced because of what I've promised you, that the functions are going to be truncated, so everything else doesn't give you any information. You get to look at any set of responses possible. And I need to argue that actually the probability that you see these values on those inputs in your function is going to be almost the same in the case when you were actually just a regular telegram random DNF from the ones where some coordinates were flipped. And the way we're going to do this is actually by proving something a little bit stronger. We're going to say that even if f gave you more information, even if it told you which clause was the first one to be satisfied in this random process where we generate one random conjunction at a time, if it tells you which conjunction was satisfied first, this gives you actually more information. So somehow, in a way, it should be even easier to distinguish the yes and no case if I give you more information, but we're going to argue, no, actually, in a very formal sense, even in this extra information, the two distributions look nearly identical to each other. So let me actually define this properly. What I'm going to introduce here in terms of terminology is this idea of a signature of Talleyrand's random DNFs. So here, maybe the example is the best way to look at it. It's this idea that you chose some sets of inputs, x, and I'm going to choose Talleyrand's random DNF, and either I've chosen a set of coordinates to flip, or I haven't. So it's either going to be monotone or it's going to be anti-monotone in some of the directions. And now I'm just going to start drawing the clauses, the conjunctions, and telling you the value of those conjunctions on each of the inputs. So I draw the first conjunction, and here in this example, it just takes the value 0 on all the inputs. So you get to learn that actually the first conjunction I drew, you don't get to know what this conjunction is, but you know that it evaluates to 0 on all the inputs that you had. The second one here in the example that we have, we learned that actually it evaluates to true. It's satisfied by the second input, but it evaluates to 0 in all the other cases. So if we just focus on this second input, what this tells us is, in particular, for one of the things it tells us is that if I'm in the case where I drew my function from the yes distribution, all the bits in C2 must be contained in the ones of x. So the only coordinates in this second clause must be either the second, the fourth, or the fifth coordinate in this example. On the other hand, if I flip some of the coordinates, it could be that I picked the conjunction could be 2, 3, and 4, but I happen to flip 3. So somehow we're going to try to use this to distinguish between the two, but building this lower bound, we're going to argue that actually this is impossible. Now if we continue, we pick the third clause. Here I'm making one tiny change from what happened so far. I'm saying, well, we already know that the second input was satisfied by one of the clauses. So in particular, we know that f of x is going to be 1, so I'm not going to tell you any more information about this input. So all you're going to learn is that, well, for this third clause didn't satisfy, none of the other inputs satisfied it. And then we continue this way until we've given you information about all the different clauses that we have. And at the end, this gives you strictly more information than just the value of f, because if you know which clauses, or if you see the interior section of the table, you can actually compute the value of f of x on the right-hand side. It's just the or of each row. Okay, so this is now this idea of this signature, this idea of giving more information about which function I drew, or which random DNF I drew. And this now is the formalization of the stronger statement we're trying to show. Before, we were trying to say that any set of responses where the responses were just the value of f on all the inputs, they had the same probability in both cases. Now the stronger one is saying actually any signature that you could possibly get, any of those tables that you could fit, that you could define in the same way that we defined it. So any legal signature that you have the same probability of seeing the signature from a set of clauses, whether you took the input as is or whether you flipped some of the coordinates. So now we get kind of to the second reason why these random DNFs are so nice. The first one was that they were very noise sensitive. So this was very useful for us to be able to say that we can flip very few coordinates and actually get something useful out of it. The second reason this is really nice is because now, once we're in this setting where we're looking at signatures, we observe that actually all these columns, the value you get is completely independent of what happened in the previous columns. We have all these independent events. So now when we're asking, okay, what's the probability that all these columns were of all these different types that happen to match this matrix I'm looking at? This is just the product of the individual probabilities that you observed everything in, you observed the first column the way you see it in the matrix times the probability that the second column matches exactly what you wanted or what you expected, and so on down the line. So now we've kind of simplified the problem. Instead of just talking about this somewhat rich class of functions of DNFs, we're now talking about conjunctions and how they behave when we flip some coordinates or don't flip them at all. And what we can show is that actually for every column type, you're going to have very similar probabilities in both sides. So formally, we're going to look at two different settings. The right way to think about this is this idea that actually most of the columns in a signature matrix are going to be all zeros. They're going to be all zeros or zeros and stars together, simply because there can be at most one column that includes a 1 for each of the rows. So there's at most q of these columns that are going to contain a 1. The rest are all zeros, or again, zeros and stars. So it's actually very useful to split the analysis into those two cases, because now what we need for the all zeros case, we need a much stronger inequality than in the alternative case, the case where you have some 1s in your column. Again, this is simply because we have so many of these all zero queries. On the plus side, however, it turns out that it's also a bit easier to analyze the case when it's all zeros, so we can actually obtain one of these strong lower bounds. So here, the key term in this inequality, the first one, is that not only do we show that this probability of observing the zero column in the yes case is 1 plus little o of 1 of the probability of seeing the 0 when we flip some coordinates, but actually we do something much better than 1 plus little o of 1. We do 1 plus little o of 2 to the minus square root n. So once we have this really, really close connection between these two probabilities, we'll see in a second how this is exactly what we needed to actually get the overall probability. But for now, let me just say, in the sum 1's case, we also get the inequality that we need, which is a bit weaker, but which is perfectly sufficient for what we need. Both of these arguments are essentially, at the heart of it, just counting arguments to show that the number of conjunctions that satisfy the correct requirements is roughly going to be the same, whether or not you flipped some of the inputs. And then this is the one equation slide that says, okay, once you've done this, you've actually done everything. The first line just says, okay, exactly what we said. This proposition said we can take this this and inside and just take the product of individual probabilities, split up the product into the two cases where you have the zero columns and when you have the columns that have some 1s, and then plug in the two inequalities that we had in both cases. And here we see that actually this is where we needed this very strong inequality. We have so many of the terms, so many of the columns that have zeros, that this difference that we had, I think I'm missing one extra parenthesis here, is going to be blown up by a factor of 2 to the square root n. So this happens to exactly cancel out the approximation parameter that we got. And in the end, we get exactly just what we were hoping for, to say that the probability you saw the signature in the yes case and the no case are almost identical to each other. So no adaptive algorithm will be able to distinguish between the two. And in particular, no algorithm will be able to distinguish between monotone and non-monotone random Talleyrand DNFs. And that's it. Once we've had this, we have the lower bound. And combining it with the best upper bound that we have, we're now in a situation where we have a reasonable gap that's only quadratic between the best upper and lower bound for general adaptive algorithms. So roughly square root n is the upper bound, and roughly n to the 1/4 is the best lower bound that we have. So just in closing, I just kind of want to mention two questions that are fairly obvious, but just to make a few comments on them. The obvious open problem here is, can we please close this gap? My guess is that the square root n bound is the correct one, and then this should lead to the question of, okay, so why do we get n to the 1/4? Which step in the argument do we need to sharpen if we were to try to prove this optimal lower bound using the same approach? And this is where I have a somewhat unsatisfactory approach. it turns out that n to the 1/4 popped up in a few different places. I want to say almost every argument that I've swept into the rug, you naturally see a point where n to the 1/4 shows up, where if you have q to be set to n to the 1/4, everything cancels out nicely, and works out so that the parameters give you the condition that you wanted, but we can't push it any further. So somehow this is kind of one of the interesting questions of, is there something interesting going on here, or is it just coincidence that for different technicalities, this value was the one that popped up? And at this point, I don't know. I really don't know. And the second open problem that I just wanted to close with is kind of a reflective of the bittersweet nature of this result in a way. I mentioned that this problem was one of the problems that attracted me to property testing in the first place. And it's also one that I used shamelessly to recruit other people to work in this area, because it's a great problem to state. It was a great problem to state when I first learned about it, when you can easily describe the problem and then say, and listen, the best upper bound we have is n, and at the time the best lower bound we had was log n. So you have this huge range where you make any improvement and everybody's going to be really excited, and how hard can it be? Because it's just monotonicity testing. So this was a great hook to actually get people interested in these types of problems. Now that we have a quadratic gap, it's a little less, it doesn't sound as obvious that this is a great teaser question. So then there's this question of, okay, what is the next obvious, embarrassing, easy-looking problem that we could use to replace testing monotonicity? How can I continue to get people interested in this area with this tantalizing problem? The one that I have, which is my current favorite, is testing triangle freeness. This is something we can define in graphs, and also something that has natural analog for Boolean functions. So this one is also very nice because the best lower bound we have, now both the upper bounds and lower bounds are in terms of epsilon instead of the dimension, but the best lower bound we have is some polynomial of 1 over epsilon. I forget the exact polynomial, say 1 over epsilon to the 20. And the best upper bound we have is a tower of height only logarithmic in 1 over epsilon. So we have tower type and we have polynomial, and we really don't know where the answer is. This might be the next obvious problem, but I'd love to find more of these problems where we have huge gaps and we don't know why. And somehow this could tell us something new about fundamental classes of Boolean functions. I think that's it. Thank you very much.
Now we have some time for questions, so.
Yeah. Hi, thanks a lot for the talk. My question is, so you defined the distribution for the Talleyrand random DNFs, and you studied their properties. Do you think that is sort of the right distribution? Because you mentioned at the end that that the n to the 1/4 seemed to constantly pop up in the analysis. Is there maybe some other distribution that you looked at and think that maybe that one would get the n to the 1/2 lower bound, or is that the only distribution you've looked at?
That's a great question. In many ways, this Talleyrand's random DNF is extremal in the set of monotone functions. It's like the extreme way for noise sensitivity and also other parameters. It's natural to think that this might actually be the hardest class of functions for which we can build these distributions and prove lower bounds. I don't think I don't have any reason to believe that our analysis is tight beyond these coincidences. So it wouldn't surprise me if this can actually be improved for this class of functions. It's also quite possible that actually the analysis would be much easier, or might actually require different classes of functions. This would be also really, really interesting if that was the case, but I also have no idea what these functions would be, what you would want to use. So yeah, that's a great question.
Thanks.
Related to that, do you know if your bound is tight? If I just consider such functions, is the bound tight?
No, I don't know that. No, so even just for the monotonicity testing problem, restricted to these random DNFs, I don't know that that the lower bound, I don't know that we can do better than the current general monotonicity tester. So yeah, so that would be perhaps the obvious step to try to do this, is to either show that we can improve the upper bound in any way, even a little bit from this general upper bound. This in itself would also be really interesting.
Hi. So there is this proposition that you said that if a function is noise sensitive and you flip some of the bits, then it becomes far from monotone. Is it something easy to see? Kind of said it sounded easy. Is it?
Yeah, it's not difficult. So the full proof is in our paper, but I don't want to take credit for this. That level of it must have been known as well before. I'm trying to figure out if I can say in one word why that is. And I think the way to picture it is to say noise sensitivity is defined over random inputs. So let's just pick an input where we fix everything except the set of coordinates that we're going to be flipping. So now if you look at the restricted function in this case, we're actually going to see that, well, in one case it was monotone, and the other one it's far from monotone. So somehow changing those values in this restricted function, you're going to be far from monotone with good probability. So for most inputs, fix everything outside of S and look at the function inside of S. It's going to be far from monotone in this case, because one was monotone, the other one is anti-monotone. And now you do this over every x, and you're going to see actually for many x's this is the case. And if you wanted to turn your function into a monotone one, you'd have to fix the restricted function at each of those individual places. And so the cost of fixing the function even locally, even just so that locally those little functions are all monotone, that's still going to be very expensive. So I think that's the high-level view of why that's the case.
So basically you're saying if it's monotone, it has to be monotone in any slice. And you're showing us that most slices are very far from monotone because they're the inverse of a balanced, kind of balanced monotone function.
Except not necessarily on slices. I guess on subcubes is what I'm picturing.
Yeah, that's what I meant. So
yes.
right.
Yes.
You fix some coordinates. Yeah.
Yeah, exactly. So you fix some coordinates, you end up with a subcube. The function in one case is monotone. On the other function, it's anti-monotone. Now the noise sensitivity tells you that not only is it monotone versus anti-monotone, but it's not all going to have the same value. Like it's not going to be close to being balanced, so it's far from monotone locally. Yeah.
Great, thanks. Any other questions? I'm actually curious about the last slide, the technical slide. Can you say again? You mentioned briefly how you use, well, what kind of independence you use. How do you manage to get the first equality there? I was a bit confused by that.
So this is the proposition we use, right? The independence that I'm using is simply the fact that in my construction process, I draw each conjunction independently. So this means that now, once I look at the signature, if I'm trying to match all the columns, and I look at them one by one, what happens with the new column should be independent of what happened before. I guess except for stars, but that's something that's trivially satisfied, I guess.
I guess the stars is what confused me. So for you, all zeros includes stars.
Yeah, so somehow this is where I'm oversimplifying things because I keep on thinking of stars as something I can just ignore. So yeah, so the all zeros means all zeros are stars in this case. So yeah, so I think the formal statement would have to be refined a little bit to say this probability that you satisfy all these columns is the same as the product when I restrict the columns to the non-star rows.
Thanks. Still have time for one last question.
Oh, it works?
Yes.
Yeah, so I think in this proposition, independence is over the choices of the clauses, right? The
yes.
little ci's are fixed, so if it's star, 0, 1, it doesn't matter. The clauses are independent, so you shouldn't think of whether it's a star or a zero, or at least I don't think. I mean, it doesn't matter what's written in the little CIs. What's important is that the clauses are independent. No, isn't it?
That sounds right. And
or maybe previous CIs because of the stars. Whether there was a 1 there, the next will be a star. I'm not sure.
So I want to agree with you because it means that what I've written is correct as is. I'd have to go back to the paper to double check. But yeah, so somehow there is this very strong form of independence, and it might even be, if I could think on my feet, I could tell you if it was actually true independence or not. Yes.
So if there are no other questions, let me thank everyone for joining again. And this might be the last session of this spring, and we'll hope to see you all in the fall. Feel free to send us more suggestions. And thank you again, Eric, for this great talk. Everyone is welcome to stay. You can ask more questions kind of offline, or just take the YouTube broadcast offline. So everyone is welcome to stay, ask more questions, and thanks again, everyone.